Thank you all for coming to my talk, Leibniz, a generics-based expression simplifier. My name is Anthony John Ripa from Stony Brook University's Computer Science Department. First, a required introduction. Then, I'll start by motivating the problem. I'll discuss prior work. I'll refactor prior work into a rule-based system. I'll discuss how to think about this approach. Finally, I'll discuss future work. Introduction. Expression simplification can be thought of as coming in two flavors: algebra and calculus. Algebra is naive, and algebraic simplification may produce expressions with removable discontinuities, such as x over x simplifies to 1 if x is not 0, else undefined. Calculus is sophisticated and is set up to deal with these special case removable discontinuities with limits. Instead of having two different approaches to be used in two different places, we seek a unified approach. We introduce a new primitive called a generic. We use generics where we would otherwise use variables. If x is a variable, we saw that x over x was piecewise. If x is a generic, x over x just simplifies to 1. Instead of algebra creating removable discontinuities, followed by calculus promptly removing them, with the appropriate primitive, we simply avoid creating the removable discontinuities altogether. This makes problems easier to solve because the primitive is simpler and avoids needing to treat burdensome edge cases separately. Motivation. First, symbolically. Historically, applying the rules of algebra strictly to problems in calculus has led to contradictions. Consider the relatively simple h over h at h equals 0. Starting in the middle, we may go right. H over h at h equals 0 is 1 at h equals 0 is 1. Alternately, we may go left. H over h at h equals 0 is h at h equals 0 over h at h equals 0 is 0 over 0. The same rules applied in different orders yield different results. Consider a calculation of the slope of the tangent line of f of x equals x squared. We may try to find that slope by simplifying the difference quotient at 0. Simplifying the inside first, we get a factor of h over h. We replace with 1. We cancel 1. We evaluate yielding 2x. We correctly found the slope is 2x. Let's apply the same rules in a different order. Distribute evaluation over top and bottom. Evaluate. Subtraction yields 0 over 0. Since two different answers were gotten by the same system of rules, the system was considered not well defined. The problem was dispensed with by disallowing division by 0 in any and all forms. So our starting expression was said to be undefined. This short calculation of the slope of the tangent line yielding 2x was labeled an invalid derivation. Now, geometrically, the motivating problem is still that of finding the slope of the secant. As you may remember from geometry, a secant is a line that touches a curve in two places. Our curve is the blue curve, also known as f of x equals x squared. Our secant is the red line. To get the slope of the secant, we do delta y over delta x. In our case, delta x is h. We calculate delta y as f of x plus delta x minus f of x. In our case, delta y is f of x plus h minus f of x equals x plus h squared minus x squared. We calculate delta y over delta x as f of x plus delta x minus f of x over delta x. You may remember this from calculus as the difference quotient f of x plus h minus f of x over h. So if we simplify, delta y is 2xh plus h squared. Delta y at x equals 1 is 2 plus h times h. Delta y over delta x is 2 plus h times h over h. Here's a graph of the slope of almost all secants at x equals 1 as a function of h. For example, if we let h equal 1, then we read off the graph the slope of the secant is 3. Now we have the slope of almost all secants. As you may remember from geometry, the tangent line is a special secant where the endpoints overlap, i.e. h equals 0. We want to read the slope of the tangent line off the graph by reading at h equals 0. Unfortunately, f of 0 is undefined. Calculating f of 0 has traditionally required an entirely new branch of mathematics, i.e. calculus, just to get 1 point. Finally, here is the slope of all secants. It is surprising only in its lack of surprise. All we truly did was to omit the cartoonish circle that we manually added to the previous graph. Current mathematical techniques require the college-level heavy machinery of calculus with the limit of the difference quotient. This special case reasoning is unbelievably complex, and it should not be believed. The intrinsic complexity of this problem is smaller than the extrinsic complexity of current mathematical techniques. While it may be true that some discontinuities require special care, removable discontinuities should not be carefully removed, but instead never manifested. Prior work. Prior work originates with Al-Khwarizmi's The Compendious Book on Calculation by Completion and Balancing, from which we get the word algebra. Later, Fermat's method for the study of maxima and minima introduced the concept of adequality, which was something like effective, approximate quality. These treatments can solve problems that today would be considered calculus problems. Inspired by Fermat's work with adequality, Leibniz published his new method for finding maxima and minima. Also inspired by Fermat's work with adequality, Newton published his Principia Mathematica, which included differential and integral calculus. Fourier's analytical theory of heat would introduce transform techniques, which transform problems from a less favorable space to a more favorable space. Later on, we would have publications like Heaviside's on operators in physical mathematics, replacing continuous with discrete methods. Prior work implementations include the inconsistent results of computer algebra systems, such as Maple. What does Maple simplify 1 plus h minus 1 over h to? The answer is 1. Even when evaluated at h equals 0. But Maple is not consistent. If I enter 1 plus h squared minus 1 squared over h at h equals 0, Maple errors out. A handful of examples demonstrate Maple's strategy. Maple will automatically remove or combine like terms. The like terms in h over h will be removed, yielding 1. Similar for h to the 7th over h to the 5th. As well as h plus 1 to the 7th over h plus 1 to the 5th. The like terms in 1 plus h minus 1 are removed, yielding h, then h over h to 1. So, evaluating at 0 just evaluates 1 at 0, which yields 1. H plus 1 squared has no default transformation, so 1 plus h squared minus 1 squared over h will only change the 1 squared to 1. Then, evaluating that at 0 is a division by 0 error. This strategy is not just a problem for substitution. It removes the ability to correctly determine if a function is continuous. We also try the same problems in Mathematica to see how Mathematica performs. As we can see in the figure, Mathematica performs similarly. We also try the same problems in MATLAB to see how MATLAB performs. As we can see in the figure, MATLAB performs similarly. Main. We introduce a new class of semantics with meaning directly grounded in generic quantities. This semantic class will not defer to arithmetic for its meaning. Consider x plus x equals 2x. This statement is true because whenever a thing is added to itself, there are two of that thing, so x plus x equals 2x is true. Arithmetic is not used to confirm the statement because that is not the intention of this new semantic class. Consider x over x equals 1. How many quantities per quantity are there? The answer is 1, hence x over x equals 1. This statement is judged true. This semantic class seems to have a corresponding visual interpretation. If we consider how many steps we rise for each step that we move to the right, then the answer is 1. Hence x over x equals 1. The slope is considered to be 1. Similarly here, if we consider how many steps we rise for each step we move to the right, then the answer is 2. Hence 2x over x equals 2. The slope is 2. Normally x stands in for a particular number, or rather any particular number. We verify that an equation is true by verifying that the equation holds after particular numbers are substituted for x. This kind of x is usually referred to as a variable. The name variable signifies that it is not one particular number. In our paper, the meaning of x is not identical to that of a variable. x is not intended to vary over different particular numbers which may be substituted for x. X is intended to be a quantity. It is not a particular quantity, it is a general quantity. We merely think about what would be true for a generic quantity. Implementation. Leibniz is a rule system for expression simplification written in Prolog. Leibniz is named after Gottfried Wilhelm Leibniz, one of the inventors of calculus, who used algebraic notation for his calculus. The pivotal rules are: simp of 0 over 0 is fail. Simp of x over x is 1. If 0 over 0 is encountered, then this branch fails. If x over x is encountered, then replace it with 1. We retried the previous problems in Leibniz. As we can see in the figure, Leibniz correctly handles both traditionally indeterminate forms. Discussion. A natural first question is whether rewriting will terminate. Any language with both an abstraction and application operator is Turing complete and will manifest the halting problem. Generic rewriting is guaranteed to not terminate for some inputs. Confluence, also known as the Church-Rosser property, means that if A reduces to both B and C, then both B and C reduce to some D. This formalizes a notion of path independence. Confluence has been considered the default desirable property, so that when systems appear to violate confluence, rather than working with non-confluent systems, the original expression is labeled undefined. For example, h over h at 0 is undefined to preserve confluence. Calculus is overcomplicated because of the high price paid to preserve confluence. Relaxing confluence allows algebra to inexpensively solve what would otherwise be calculus problems. Confluence guarantees, among other things, that leaves will be equal. For example, we won't get 1 equals 2. In place of confluence, we seek a guarantee compatible with more use cases. The property, called lossless, will guarantee that no solutions are lost. The correct answer will belong to the intersection of all reductions. For example, 0 over 0 has extra solutions, but includes the correct solution. Generics have a well-defined division operator. X over x equals 1. Generic expressions that involve only the operators plus, minus, times, divide yield reduction graphs that are confluent, therefore lossless. Generic expressions that include an evaluation operator yield reduction graphs that are not confluent, but are lossless. As generic expressions always yield lossless reduction graphs, we offer methods for lossless graphs. Lossless meant that solutions are not lost. The naive approach is merely to intersect all solutions. The solutions to 0 over 0 is the universe. The solutions to 1 is 1. The intersection is 1. This approach may be expensive, but its correctness follows immediately from the definition of lossless. Backtracking arises in numerical stability. If an approach becomes numerically unstable, you may backtrack and apply a more stable approach. To simplify h over h at 0, the left branch yields 0 over 0. Confluence would imply the original expression was undefined. However, lossless concludes this particular test is inconclusive, so backtrack and try a different path. Simplifying division first, I get 1 at 0. Continuing, I get 1. In fields of active research like linear algebra, numerical stability abandoned embracing inconclusive tests in favor of backtracking, while supposedly completed fields like elementary algebra did not, inviting calculus to make up for its shortcomings. We may use numerical stability and backtracking in elementary algebra, just like linear algebra. This is better than hidden numerical stability and backtracking found in calculus laws like L'Hopital's rule and limit laws in general. Instead of exploring all branches, by imposing rule ordering, we can always select the correct branch. In our case, the correct branch order is simplify before evaluate. In other words, with h over h at 0, we must simplify h over h before applying evaluate. This way, we always obtain the correct answer without backtracking. The closest prior work to generics is formal variables. The main difference between formal and traditional variables is how they treat the equation x equals 0. If x is a traditional variable, then this equation has one solution. If x is a formal variable, then this equation has 0 solutions. This is because traditional variables can vary, whereas formal variables do not. For formal variables, x equals 0 is false. Formal variables are good for modeling x's in situations where x is not solved for, like in generating functions and polynomial rings. They support addition, subtraction, and multiplication, which are perfect for rings. However, formal variables do not provide native support for a division operator. This ensures that evaluation distributes over all other operators, ensuring confluence. Unfortunately, this design consideration also removes the possibility of native support and forward compatibility with calculus. In light of generics, we re-examine limit laws with an example. The limit as h goes to 0 of h over h. We tentatively distribute the limit operator over the division operator. We take the limit of top and bottom, yielding 0 over 0. We conclude the conditional equality is false. We start over. We divide h by h, yielding a limit of 1. Finally, the limit of 1 is 1. Limits are a way to simulate backtracking while remaining confluent in name only. In light of calculus, we re-examine generics. Removable singularities are removed by replacing undefined points with limit points, yielding a continuous function. H over h is the model removable discontinuity. By defining h over h as 1, generics merely combine multiple traditional steps. This guarantees generics maintain traditional answers. Transform techniques are often touted for their ability to transform a problem into a space where it is easier to solve. In practice, even if harder, a hidden benefit is that people allow themselves a level of informality that they don't allow themselves in the original space. Basically, to solve a problem without rule breaking, they take a detour through a red light district where they can bend rules, then return with clean hands. Alternately, we can get all the benefits without leaving home by recognizing x over x as 1 in the original space. We recognize shortcutting a transform in machine learning as the kernel trick. Future work. Structures. Because we have cast this as a term rewriting problem, Prolog was the natural programming language choice for implementation. Had we wanted to use structured programming, C, C++, Java, etc., we could have created corresponding structures and methods for those structures, i.e. classes. One advantage of this approach, with its abstractions, is that it can be relatively syntax independent, similar to the way in which structures from linear algebra, like matrices and associated methods, can abstract away syntactic idiosyncrasies, such as variables and variable names. Future work should include a structured approach. We have two different kinds of problems. The first is simplifying expressions, like 2x over x. The second is solving equations, like 2x equals x. We use two different semantic primitives, generic and variable, both use the syntax x, to solve those two kinds of problems. What about mixed semantics? Writing down the derivative earlier, we used only generics. However, we may want an implicit definition of the slope m, as in m times h equals h. Here the h is a generic, while the slope m is a variable that varies until the equation is satisfied, yielding m equals 1. Looking back, Fermat's first work with add equality in The Method for the Study of Maxima and Minima was a problem of mixed semantics. Thinking ahead, the entire field of differential equations requires mixed semantics. Future work should include mixed semantics. This code is available on GitHub. From there you can run the code directly in the browser. You can recreate the examples that we went over, or try more complicated examples, like this one. Thank you for your time.